To have Alberto Cattaneo, all the way from Switzerland, and we will be speaking about Poisson structures from corners of field theories.
Okay, thanks. Okay, thanks for the invitation. And okay, oh, second. Oh. Okay, and well, invitation to this interesting conference. Unfortunately, I could join only from yesterday afternoon. And okay, so well, my talk will involve some Poisson, some supergeometry, and it's based on, let's see, oh, this works. Okay, it's based on some joint work with several people. Okay, the starting point is Pavleniov and Nikolai Reshetiki, and then some development that we'll discuss today with Giovanni Canepa and Michele Schiavina, who are both my PhD students. So this will be the last part about well, 3+1 dimensional gravity. So here is just a picture of the general philosophy that I will very briefly discuss, just as a motivation. So the idea is to study field theory, quantum field theory, but first classical field theory on manifolds with boundaries and also corners, and possibly also higher codimension strata. So the idea is that whenever you have a field theory, the idea is that, well, to boundaries, you should associate some Hilbert space of the theory, and to the bulk, some operators from, well, so from states to states. And the idea that if you add, well, if you have corners, like in this picture, there should be something that you should associate to corners as well. Now, let me discuss both pictures. So probably the quantum picture is probably easier to discuss, even though it's more difficult to achieve, but easier to discuss because it's just linear algebra. So in the quantum picture, you expect to associate some vector space to the boundaries and some vector to the bulk. And what you expect to associate to the corner is some algebra that acts on the vector spaces. So if, for example, if you this picture here, let me suppose that the boundaries are one-dimensional, this sigma 1, sigma 2, and the corner is this point here. So you expect to associate some algebra to the corner C that acts on both Hilbert spaces associated to the two boundaries, and the idea that you can glue boundaries along a corner just by taking the tensor product. I'll see the picture here, by taking the tensor product over the algebra. Okay, at the classical level, instead, you should think to associate, well, instead of symplectic, have a vector space to the boundaries, you expect to associate some symplectic manifold to the boundaries. And then what you expect to associate to the corner is something like a Poisson algebra. And so the idea is that you should think of, I mean, the symplectic manifold to the boundary as some sort of symplectic realizations for the Poisson manifold you should say to the corner. And when you compose two boundaries, you should just take the product of the two symplectic manifold over the common Poisson manifold by doing some coisotropic reduction. Okay, so this is somehow the general philosophy, and the point that in some example you can really achieve it both at the classical and the quantum level. One caveat is that here was describing the simplified picture where to the corner you associate a Poisson manifold. Typically, it's not be a manifold, it will be singular, and even more typical, it will not be a strict Poisson structure, but it will be a Poisson structure up to homotopy. Okay, so now let me start with the super geometry description of Poisson manifolds. I think this should be known probably to most people here, but let me go quick. Actually, I think it was actually created by some people here. So the idea is that, okay, in the Poisson geometry, you have a manifold together with a bivector field pi, so a sector wedge 2Tp, which commutes with itself using the Skautner noise bracket. Or equivalently, say that it's the associated bracket on function satisfy the Jacobi identity. Now, the idea is to think of multi-vector fields on your manifold as functions on the cotangent bundle of the manifold shifted by 1. And so in this case, the bivector field corresponds to some function of degree 2. So if you typically, if you call the fiber coordinate p, these are coordinates of degree 1, you take the function 1/2 p contracted with pi contracted p and p. This gives you this function of degree 2, and the Skautner noise bracket is replaced by the canonical Poisson bracket on this cotangent bundle. Now, a generalization is to be a bit more flexible for example, no longer assume that P is a manifold. P could be a supermanifold itself. And so the generalization is actually starting from this data here, namely a Poisson bracket of degree -1 and the function of degree 2 that commutes with itself. So these are the data here. So M now is a graded manifold. Omega is, okay, probably don't know. Omega is a symplectic form of internal degree 1, and S is a function of internal degree 2. And we require that a Poisson commute with itself. Okay, now in general, since the symplectic structure is odd, you can realize this symplectic manifold as a cotangent bundle shifted by 1, where in general this N will be a supermanifold itself. Okay, in some cases, of course, like this one is a non-graded manifold, but typically it's a graded manifold by itself. Okay, then anyway, a function on M corresponds to some multivector field on N. Okay, but now the only condition that this multivector field will have total degree 2. So degree S equal 2 means the total degree is 2. So that means that this pi now will be a sum of a function, a vector field, a bivector field, and so on. So it denotes by pi k the k vector field in this linear combination, and the condition that the internal degree of the k vector field is 2 minus k. Okay. Now the condition that pi commutes with itself corresponds just to all these conditions. Say that I think probably should be something. Okay, pi 0 commutes with pi 0, but this is trivial. Then pi 0 commutes with pi 1, pi 0 bracket pi 2 is 1/2 pi 1 pi 1, and so on. And you get all these conditions. So the condition we had before was that pi 2 bracket was equal to 0, but this was true just because we didn't have all the rest. Okay. Now, what you can do, you can anyway associate multi-bracket on function using these multi-vector fields. You can, in this example, you can actually do it directly. You just plug in differential of function, as many as you can, or you can use the derived bracket construction. Well, in the case of just pi 2, this was introduced by Konrad-Schwarzbach. In the general case, this is due to Ted Voronov. I will go back actually to the more general version that Ted introduced in the next slide. But here is just that, okay, I have this bracket with 0 function, which is just a function pi 0. The bracket with one argument, function f, you just apply the vector field pi 1 to a function f. The bracket with 2 arguments, you just now you start have to do with these iterated brackets. Okay, you take the bracket, the bivector field with the first function, this gives a vector field, and then you take the bracket with the other function, this gives a function. Okay, now these conditions here imply that what you get here is an L-infinity algebra structure on the algebra of functions. And moreover, this is compatible with the graded commutative structure here, in the sense that all the brackets are multi-derivation. So this is what at some point was called the P-infinity algebra structure. Now, the main point here is to observe is that the choice, I mean, I told you that M can always be written as a cotangent bundle of some N, but the choice of this N is not canonical. I mean, unless you have a very special case where you only have coordinates of degree 0, 1, then there is a canonical choice where in N you just put coordinate of degree 0. So N is just an ordinary manifold. But in general, there is no canonical choice. And even in that case, you may have other. In the case where you only have coordinate degree 0, 1, you have other choices. I mean, there is a preferred one, but it's not the only one. So I will call this choice of N here, and this realization as a polarization of M. And now let me give you 2 examples. So one is the example we had before. You start with an ordinary manifold M. So this curly N is M itself. Then you take the cotangent bundle shifted by 1, and you interpret the bivector field as this function of degree 2. So this is the first example I described. Now let me give you another example. Take a Lie algebra. Its dual is a Poisson manifold. And so you can do this construction here. So you can take this cotangent bundle shifted by 1 with the induced function of degree 2. And so these correspond to the constant Kirillov constant Poisson structure, and it's just a particular case of example 1. But actually here you can see that you can rewrite these as a cotangent bundle shifted by 1 or G itself shifted by 1. This is just another way of rewriting this cotangent bundle. Okay, so this is another allowed polarization, and in this allowed polarization, the functions on the base now are the exterior algebra on the dual the function of degree 2 now is interpreted just as a vector field of degree 1, which corresponds just to the Chevalier-Eilenberg differential. Okay, so these are two different polarizations of the same structure. One gives rise to the Kirillov constant Poisson structure. The other one gives rise to Chevalier-Eilenberg differential. Okay, but they correspond to the same graded symplectic manifold and the same function of degree 2. Okay, now let me just mention an algebraic version of what I did here, well, on the previous slides, which actually can be a bit more general. So the idea is the following. Take a splitting of your algebra. Now take the algebra function, but to be more general, I did it. But take our example and split it in the sum of two subalgebras, P and H. So the condition is that both are Poisson subalgebras, but in addition, I want H to be abelian, namely under the Poisson bracket. Okay, and then, well, since you have this splitting, you also have a projection from the whole algebra function to H, and then you can define the iterated bracket is here. So, for example, you have your function of degree 2, right? So you have a bracket, say, with I argument. So you take the bracket of the function S that is given with the first function. Then you take the bracket. So these are all elements, sorry, in H. These F1, H. So you take a bracket of S with some first element of H, then the bracket with the second one, and so on. You keep taking brackets. At the end, you're not in H, you're in here, but you have the projection, so you can project down. Okay. And then, well, what I showed that under this condition, you produce an L infinity algebra structure on H, okay, on this subalgebra H. In particular, it consists of multi-derivations. And the interesting thing is that, well, this can be generalized to other algebras. And in particular, in our case, one interesting generalization would be where we no longer have really a symplectic structure, but we have a degenerate closed to form, which will appear in examples. Okay, now let me come to one further generalization, namely, I still with this triple graded manifold, symplectic structure, and function that Poisson commutes with itself, but now I change the degrees. Okay, now I will say that my omega is some internal degree n-1, and my S is some internal degree n. Okay, the reason for this difference in degree, I mean, the previous case was n equal 2, right? Omega is degree 1 and S has degree 2. But the reason to have like the difference in 1 between 2 degrees is simply that I want the Hamiltonian vector field of S with respect to the bracket to have degree 1 in all cases. Okay, this is what is natural, because then I can think of this as some cohomology. Okay, now the Hamiltonian vector field has degree 1, and moreover, this condition implies that it's a commute with itself. So this is what is called a chromological vector field. And then there are several, okay, all these structures are interesting and they have application, for example, in physics. So what I described before was degree 2. This corresponds to Poisson structure or Poisson structure up to homotopy. But the other case is also interesting. So the case degree 0 is what is called BV, and is important for the perturbative formulation of functional integral in the presence of symmetries. And the case in degree 1 is called BFV, and is important because it gives a cohomological resolution of symplectic reduction. And in field theory, this is important for the boundary of the field theory. Now, I mean, we use this terminology since 0 is BV and 1 is BFV, then, well, we can have this terminology that in case 2 we speak of BF2V, and degree 3 BF3V, and so on. Okay, and BF3V is actually related to Courant algebroid, and or also up to homotopy. I think Dima is the expert here. Okay, I will not talk about BV in this talk, but I will mention BFV because it's important for what I want to do. I actually want to describe the relation between BFV and BF square V. So BFV means the degree of symplectic structure is 0 and the degree of the function is 1. Okay, now the first remark is the following. Take the degree 0 part of your graded manifold, right, which is included as a submanifold. You can restrict the symplectic structure there, right, and you get now, I mean, the restriction is still closed and non-degenerate automatically, right? So you get a symplectic structure on the degree 0 part. Okay, so in this particular case, right, you have a degree 0 structure on your graded manifold. In particular, you have an ordinary symplectic structure on the degree 0 part of your manifold. Now, let me denote by curly C the zeros locus of the Hamiltonian vector field Q. Okay, and well, the immediate lemma you can show is that the ideal generated by, the idea generated by the image of Q. Okay, so okay. The zero locus it typically will be singular, so it's not really a manifold, submanifold. So instead, I work algebraically. I take its vanishing ideal, which is just functions that are, ideal generated by functions that are in the image of Q. This is an ideal in your algebra of functions, and it turns out that this is actually Lie subalgebra with respect to the Poisson bracket. Okay, and the proof is very short. It's just based on this simple observation that if you take the Poisson bracket of two Q exact functions, you can extract Q, right? Because when you try to extract it, you should, when the other term is, you should either apply to the other argument, but then Q is chromological, so you don't see it, and you can extract it because Q is compatible with the Poisson bracket. Okay. And then this allows you to show you that the ideal generated by image of Q is a Lie subalgebra. So this means that if C were really a submanifold, this would be a coisotropic submanifold. In general, it's not a submanifold, so we just say that this C is this ideal is a quasitrope. But then what we are interested in is in the degree zero part of curly C. And this is typically, very interesting example. It is a manifold. It is a submanifold, and this construction implies that it is a coisotropic submanifold of this degree zero.
It is always a manifold.
No, it's interesting when it is. No, it's not. No, not always, but very often it is. Very often it happens that you have an example where you want this C to be a submanifold, but this curly C is not anyway. Okay.
If it's not a submanifold and you took like the causal resolution, so that's another
yes.
manifold, can you give it like a coisotropic structure of the Wutopi?
It's contained in the. It will be one further step in this. Yeah.
Okay.
I will describe the construction going from this standard C to curly C, and of course you can apply it one step further. But you usually, you can do it. Now, the next remark is that since Q is compatible with the Poisson bracket, the cohomology of Q is not only an algebra, but actually inherits the Poisson bracket. So it's a Poisson algebra. Okay. So these are the two starting observation. And the point is that actually what you're interested in is to do an inverse construction, which more or less should answer your question. So typically you start with the coisotropic submanifold, some symplectic manifold. So here I will assume that is in degree zero, but it's not necessary. And the idea is to extend this symplectic manifold to some graded manifold, M omega, that contains it, right? In such a way that you recover this coisotropic C by the previous procedure. So mainly what you have to do, you have to be able to extend M to curly M, extend omega naught to omega, and found a function S of degree 1 that Poisson commutes to itself, and such that the vanishing ideal of the commutonic vector field of S in degree 0 gives you the vanishing ideal of C. Okay, so this was actually the construction by Batalin, Wiltkowski, and Fratkin. And let me give you the structure in a simple example where your submanifold C is given by constraints, so zeros of some function phi I. And then basically what you have to do, you have to extend here, you have to introduce some new coordinates of degree +1 and -1, the C and B. So the B will be the momenta of the C. You have as many new coordinates C as the constraints, and then you have to take their momenta to construct the symplectic structure. And your function S starts with the linear combination of the constraints times the new variable of degree 1, they're called the ghosts. Okay, and then the point that iteratively you fill in the dots so that this equation is satisfied. Okay, and the theorem is that under very mild assumption you can do this. I think this was observed by of course Batalin, Fratkin, Wiltkowski. It was made more rigorous by Jim Stashev, who also generalized it to slightly more general situation. Florian Schetz, I think, yes, something disappeared here, but yes, Florian Schetz did the construction where your submanifold is not given by constraints. You can generalize it. And Felder and Kashdan extended this construction to the algebra geometric setting. Okay. And the other observation is that not only can you do this construction, but it's also essentially unique. Okay, so this curly M and omega are unique up to two kind of operation. One is, of course, symplectomorphisms that are compatible with S. And the other one is adding trivial pairs. Now you add new, say, B and C variables, but with some trivial cohomology. This is another equivalence that you have to allow. Okay, so this is the idea. And so now the idea, the philosophy, the BVFE philosophy, which is also, of course, then taken over by the derived geometry, is that you replace your submanifold C, which sometimes is not even a submanifold, and even if it is a submanifold, usually it has a very, very bad symplectic reduction, and instead you replace it by new gadget. And the idea that basically you move from the category of symplectic manifold, coisotropic submanifold, to the category of Hamiltonian graded symplectic manifold, and there where you have to stay. Notice that just going, I mean, of course you can recover, I mean, well, there is the here that in good cases, so when you really have a reduction, you can recover functions on the reduction as a cohomology in degree 0, okay? But this is not what you have to do in general, because typically this cohomology will be very, very poor. Okay, so I mean, typically when so for example, the reduction is, I mean, is non-Hausdorff, so you only have constant functions, so this cohomology we just are. So this is not very interesting. It's really important to stay at this level. Okay. So now let me mention the new part. Well, new for us, but we introduced it like about 10 years ago. These are relaxed structures. So the idea is that, okay, let me start with this further generalization, and then I will show you why it is interesting, both as a way of constructing non-relaxed structure and because it appears in field theory. So the data now are here the following. You have a graded symplectic manifold, but now you have this omega QS, the same symbol as before because they are related, but they are slightly different in the sense that omega is a closed to form, but it's possibly degenerate. And I will take the degree to be some n-1. Q is, as before, is a vector field. It has degree 1 and it's commute with itself. So it's exactly before, a homological vector field as before. And S is just a function of degree n. And there are no further conditions. I'm not saying that it Poisson commutes with itself. I'm not saying that Q is a Hamiltonian vector field, nothing. So it's very, very loose structure. But why is it interesting? Well, because the first thing you can do is basically you can measure the error, right, from S being the Hamiltonian function of Q. So you take this difference and you call it alpha twiddle. So this would be now a 1 form of the same degree as S. So this will have the degree n. Okay, then you can take its differential. This will be a 2 form, right, also of degree n. And of course, if you use Cartan calculus, you can see that, well, you can write this either a d alpha twiddle or minus the Lie derivative of omega with respect to Q. And in general, this is not 0 because I'm not assuming that Q is Hamiltonian. But since Q is cohomological, you can apply LQ again, use again Cartan calculus to check that now Q is a Hamiltonian with respect to omega twiddle, okay, automatically. Okay, so these are the new data. Okay, alpha twiddle is 1 form, omega twiddle is a 2 form, and they both have degree n. And the idea is that now they look very similar to what I called before, well, an example of the structure called before. And the point is that, first of all, this Q is not only symplectic, but typically is Hamiltonian. So for most values of n, there is a unique Hamiltonian function as twiddle, such that which is a Hamiltonian function for Q. I mean, this was observed by Dima. Essentially, you use the homogeneous degrees to show that, well, this equation implies that Q is actually Hamiltonian, and then you will easily verify that the Hamiltonian function is unique because constants, I mean, constants should have degree 0, so you're not allowed. So for most cases, and actually for the case I'm interested in this talk, this happens. And there is also another observation that, I mean, of course, you can try to get S twiddle as the Hamiltonian vector field of Q, but it turns out that there is also another way of constructing S twiddle, which is that you just you take the original omega and you contract it with Q twice, and well, you divide by 2 to get the correct normalization, but this is another way of computing S twiddle. Okay, and I mean, this formula, well, is usually more practical, and it also has an interesting interpretation because contracting omega with Q 2 times is somehow the replacement for the Poisson bracket of S with itself. Notice that since omega is a degenerate, you cannot even speak of the Poisson bracket of S with itself because it doesn't have a Hamiltonian vector field. But you should think of Q as somehow the Hamiltonian vector field of S up to some error. And this formula here is somehow the Poisson bracket of S with itself. So from this formula, you see that S trivial is the error from the equation that said that Poisson bracket of S with itself is equal to 0. Okay, now the observation here is that now, okay, we have omega trivial, Q, and the Hamiltonian function. Now this Hamiltonian function commutes with itself because Q is chromological. So this is a very similar to a BFN plus V. BFN plus 1 V structure, degree, but the only point is that is omega trivial is maybe degenerate. So we call it a pre-BFN plus 1 V structure. Okay, but okay, if you don't like working with the degenerate structure, you can try to do a reduction. So what you do, you can take the kernel of these two form omega trivial and try to go to the quotient. I mean, if the quotient is smooth, then on the quotient you will have a BFN plus V structure, and the reason is that since Q is Hamiltonian, it's automatically projectable. It's an immediate algebraic consequence. So what you can do, you can go to the quotient, and on the quotient, you have uniquely determined data, omega underline, Q underline, S underline, that give you a BFN plus 1V manifold structure. Okay? And okay, in the application, this quotient is often well defined, not always. I mean, I will have some very important example where it is not, but very often it is. Okay, now let me come to the application of field theory. So in field theory, you start with some BFNV local data on some manifold. So okay, typically if you want to do BV theory in the bulk, so quantum field theory in the bulk, you start with the data that give you a BV theory. But I mean, I might say that I don't care for the bulk. I'm already at the level of the symplectic structure underlying the theory. So in this case, I will start with BFV data already, and so on. Okay, so let me be generic here. So we start with some BF and V data that have to be local. So that means the following, that my graded manifold omega now will have to be some space of fields on some manifold sigma. So space of fields should be essentially jets of sections of some vector bundle or well, connections and things like that. And I want omega and S as before. I mean, omega will be symplectic, S will be a function that Poisson commutes with itself, but I want them to be local. So local means that they are integral over sigma of some function of the jets of the fields defined at the points. Okay, the usual structure. Okay.
Quick question. Says, I mean, I've looked at some of these papers
Yeah.
before, but what are you doing with the fact that it's be infinite dimensional? Like, I mean, how are you making sense of this exactly?
Oh, you put some, well, depends. If you want to put some more structure, usually we want to deal with it as a Frechet manifold or the Frechet super manifold. Okay. Or otherwise, you just deal with this. I mean, the algebraic structure. I mean, you can also do like as done by variational bicomplex. I mean, it becomes more cumbersome. It's easier to present things working with the manifold.
That's fine. I just wanted to like.
Yeah. Yeah.
Okay,
yes. The problem is that you're forced to work on using Sinfinity, both because essentially, well, super manifold do not work well in the CK case. And moreover, typically all these things appear, well, because you're describing symmetries that involve the derivative. So you're really stuck with the Sinfinity case. So the best you can do is to put a Frechet structure. You can put a Banach structure, but they're nice Banach spaces because like you have this filtration of Banach spaces going to your Frechet spaces, just adding more and more derivatives. So typically, I mean, you don't have the implicit function theorem, but you're very close to having it. So things are quite good. Okay, then what you can do, you can compute the Hamiltonian vector field of S. So actually now my omega, since it's infinite dimensional, I just assume the weak non-degeneracy condition. So weak non-degeneracy condition means that somehow there is no kernel, but I'm not claiming that it's surjective. So that means that if a function has a Hamiltonian vector field, that is unique, but not every function has a Hamiltonian vector field. So one condition here is that is S has a Hamiltonian vector field, and the Hamiltonian vector field is chromological. Okay, so okay. Now, the point is that when you compute this, when you start this equation, right, this differential of S, now really write delta S, well, not to make confusion with the drum differential of sigma, but also to stress that this is like the usual variational differential of the action. And when you compute variation, usually you have to integrate by parts because you want to isolate, right, the differential of the fields and the jets. And the point is that, okay, I mean, you start studying your theory on a closed manifold, so you don't have boundary term, and this is how you define your Q, okay? But now the point that you're interested in the case where your manifold has a boundary, okay? So what you do here is, of course, this equation no longer works, but what you do is you retain the same data you had here. I mean, you retain the same M, the same omega, the same S, and the same Q, but now this equation is violated by boundary terms. Okay, but now this is a particular example of what we described before, this relaxed structure. So now you get this alpha twiddle, which will be a one form, okay, which is measure this error, and explicitly it is written in terms of boundary integrals in this example. Okay, then you can do the previous construction. You get this pre-BFN plus 1V structure. I mean, the nice case and is where you can make the reduction. Okay, so you get this BFN plus 1V structure on some new infinite dimensional graded manifold M underlined, and you also get like omega underlined and the underline. And in good cases, this new structure actually turns out to be again a space of fields. Notice one thing that is general is that since can I go back here? Okay, since this arises in terms of boundary integrals, it turns out that whenever you just displace a field by something that vanishes on the boundary, just you take some bulk displacement of the field, you don't see it in the right? You don't see it in alpha twiddle, so you don't see it in omega twiddle. So these are vector fields that lie in the kernel of omega. So in particular, when you do this quotient, you get rid of every information of bulk fields. You just left with information on the boundary fields and their jets. Possibly, I mean, they're transversal jets. Okay. And if you're lucky enough, this reduction is not only a smooth infinite dimensional manifold, but actually a space of these boundary fields. Okay. And there is an intermediate nice case which we have to deal with because in the example it appears where you can do some partial reduction, which has the good property that this partial reduction, and we call it over bar M, is a space of fields. It's a space of boundary fields, so it's the good part. But the two form is still degenerate. Okay.
What do you mean it's a space of fields?
I mean, it's a space of sections of like vector bundles or connections, things like that. Okay. But you still have the degenerate two form, and you cannot go further because I mean the full reduction would be singular. Okay. Now most field theories are in the nice case, so we are very lucky. So I'm saying that, well, okay, you can take one example of your favorite topological, well, our favorite topological field theory like Chern-Simons theory and BF theory, but also physical theories are offering a nice case. For example, Yang-Mills theory is in the nice case, but also gravity. I mean, if you take the Einstein-Hilbert formulation of gravity, I mean the second order formulation, it also lives in the nice case. An example where you're not in the nice case is when you do the conframe formulation, which sometimes called Palatini-Cartan, Holst, I mean, various names, but that's the one where the fundamental field is not the metric, but the coframe, and you reconstruct the metric using the coframe. And in that case, it turns out that in dimension, so if you do it in d+1 dimension with space dimension larger or equal to 3, you are not in the nice case. Okay, but you are in the intermediately nice case. Okay, in dimension 2+1 is still nice because it's just a particular example of BF theory or Chern-Simons theory. Okay, but when you go already in 3+1 dimension, it is not nice. Okay, and I mean this is not just okay. Why would you want to do coframe instead of the other one? Well, one reason is that it's better for our purpose because it's first order, so it's easier to go to the corner, as I will show you later on. And the other question that you want to couple gravity to fermions, you really need I mean this formulation. Okay, so now let me come to one example, important example, Chern-Simons theory, which is nice. And actually, it's nice. Now I will start already from the boundary structure. I mean, I will spare you the bulk structure. So I start on the boundary structure. So what is Chern-Simons theory on the two boundary Chern-Simons theory on the two manifold? This is just a theory of flat connection on the surface. Okay, so that means the following. So you take some quadratic Lie algebra G. So quadratic means that you have an invariant in the product, non-degenerate invariant in the product. You take a closed two manifold, and you take, I mean, my example, we just take a trivial principal bundle over sigma with a structure group, the Lie group that integrates G. And it's just to simplify the notation. You can also take the non-trivial situation. Now, the fields here are connections for this principal bundle. So with my choice are just the algebra valued one forms. Okay, and then you have the Atiyah-Bott symplectic structure. Okay, so use this formal writing. So this delta A should be thought of like a basis of differentials, I mean, in a very formal sense. But this is the idea that, I mean, you have a pairing between two the algebra valued one forms. And this pair is, you made it symmetric and non-degenerate. Now, there is an interesting subset of a set of connection, which is a space of flat connections, right? Curvature equal to 0. Okay. And well, of course, you can think of the curvature as an equivariant momentum map. So you immediately see that this is a coisotropic, and then you are interested in doing the symplectic reduction, which means taking the quotient by gauge transformation. Okay. And now the idea, like, I want to formulate this in the BFV formalism. So in the BFV formalism, what I have to do? Well, I have to extend my space of fields. So to the A, I have to add this new variable C. Remember before I said, okay, I have to introduce as many variables as the constraints. Of course, now it's infinite dimensional. So the correct procedure that there should be the same kind of things. So somehow I should be able to see this C as somehow the Lagrange multiplier that impose the constraints. So since the curvature is a Lie algebra value 2 form, this C should be Lie algebra valued 0 forms. Okay, and then I shift them by 1. The B will be their canonical momenta. So I will take them to be not 3 forms, so the mistake should be 2 form. The Lie algebra value 2 form shifted by -1. So I can take now this canonical symplectic structure. And then remember, right, the general BFE procedure said that the function S should be the C variables times the constraints plus something to make the S commute with itself. And here you can see that this is an example of BRST kind, which means that, I mean, you just have to add one single term. You have a solution with one single term, which is just this term with 1 D and 2 Cs, okay? And you just write things down. Now, what you can easily do is to compute the Hamiltonian vector field, and I will apply it to the field. So if you think of the fields as coordinate on this infinite dimensional manifold coordinate function, so I can apply Q to the coordinate function and get some other function. And you see that Q applied to the connection gives you DAC, so it sees the gauge transformation. Q applied to B gives you the constraint up to some, of course, gauge transformation of B, and then Q applied to C just gives you 1/2 CC. So here you see a combination of the Kosul differential of some manifold and the Chevalier-Allenberg differential for the Lie algebra. So this contains both defining the submanifold M and going to the quotient. Okay, so this. Now what you want to do is say, now suppose that sigma is a boundary. Okay, what happens? Well, you see that, okay, what I have to do is to compute the differential of the function. So maybe let me go back here, right? So the first term was here, C times the curvature. So when I take the differential of the curvature, this would be the covariant derivative of the variation of A. Okay, so I get this term here. And this is where I have to integrate by parts, right? So when you integrate by part, you get the covariant derivative of C. And this was actually, right, the Q of A. You see here, but now you also have a boundary term. So you still have an integral of the boundary of C pair with the variation of A. Okay, and you see this is the only boundary contribution. So this means that the alpha twiddle in this example is just the integral of the boundary of the boundary, so the corner gamma of C delta A. Now the corner is one dimensional. So in this example, just a circle or a bunch of circles. Okay, A is a 1 form and C is a 0 form. Then, yeah, well, the 2 form now becomes as this canonical form. So this tells you that you should think of now, I mean, basically what you do here, you have to do mod out by the kernel of omega twiddle, but the kernel of omega twiddle contains basically every possible variation of B and every possible bulk variation of A and C. So what is left in the quotient are just I mean A and C on gamma. Okay, so the space of now this space I'm underlying now as coordinate A and C. So A now is still a Lie algebra valued 1 form, and C is a Lie algebra valued 0 form, shifted by 1. And I mean, you have this canonical symplectic form, which actually means that this is actually a cotangent bundle. I mean, you can, well, okay, non-canonically, but there are two standard ways of viewing this as a cotangent bundle. You can either see it as a cotangent bundle of shifted by 1 of this part, or a cotangent bundle shifted by 1 by this part. These are the two natural ways, but of course are not unique. Okay. The other thing is that you have to see what is Q here. I mean, I write Q underline now. And well, you use the previous formula. You know that Q of A was the A of C, right? And this is still, I mean, the projection is just the A of C. And Q of C was 1/2 CC. So this is the projection itself. So the only thing you have. And then you have to compute the Miltonian function for this Q. And you easily see that it has this form. It's just 1/2 C pair with the covariant derivative of C itself. Okay, so this is a function of degree 2. Now, of course, everything will work very nicely because this is an example of an AKASD theory, but okay, we don't want this is just for people who know that. Now, what I want to do is to interpret this as a multivector field with respect to some polarization. And I will take this polarization. So think the space of field as a cotangent bundle shifted by 1 of the space of Lie algebra value 1 forms. Okay, so now the base fields here are the connection A, and the fiber fields are the ghost C. Oh, what happens? Oh, sorry. So that means very, very formally, I write down these as, so now in the case, see, the base is degree 0. So I only have the bivector field part. I very formally write it down this way. Basically, I replace the ghost C by the derivative with respect to A. Okay, so you get this bivector field. And now I split the covariant derivative into the usual, the RAM derivative plus the term, the bracket with A. And so you see that this Poisson structure has a constant term and a linear term. Okay, so it's an affine Poisson structure. Okay, and probably is more instructive to see what is a Poisson bracket of linear functional on the base space. So I take so a linear function means I take a test function f. So this is the algebra valued function. I pair it with A and I integrate. Okay, so this is a linear functional of A. So you take another linear functional with now test function G, right? And I take the Poisson bracket using this bivector field, and you see that what you get is two terms. One is just the pointwise Lie bracket of f and g, and the other one is the integral of f paired with the differential of g. Okay, and so now you can should recognize this structure. Basically, what I do, I extend my Lie algebra to now to the loop algebra. So f and g are maps from the circle to the Lie algebra, and just take the pointwise Lie bracket. So this is a loop algebra of G. And then this other term here is a Lie algebra cocycle. Okay, and well, basically what this tells you here, this Poisson structure is essentially Poisson structure associated to the central extent, to the dual of a central extension of this loop algebra by this cocycle. Okay, so this gives you the usual affine Lie algebra associated to Chern-Simons theory. And well, now you can think that the quantization will be the usual vertex operator algebra. Okay, so usually this is not recovered this way, but I mean, this is an alternative way of getting like the affine Lie algebra and the vertex operator algebra associated to Chern-Simons theory. And it just like, you see, just, well, very half a page computation. Yes?
I was a bit lost here. So this M underline is the big space?
So M underline is a reduction of the space of fields by the kernel of omega 3.
It was only C and A, right?
Yes, because yes, because it's I take the A's are in here, right, and the C's are in the fiber. So it was a direct sum of two vector spaces, but I write it as a cotangent bundle shifted of one or one of the two vector spaces.
Now correspond to the function S viewed as
yes, exactly. Yes, yes, yeah. With this polarization, yeah, pi becomes a bivector field. Of course, you can choose the other polarization where you put on the base the ghosts, and then of course it's not just a bivector field. It's actually becomes a vector field. That is an example. Well, it has a function and a vector field. It has two components.
And what would you do with this? Take it the right bracket? Or?
Yes, you take the derived bracket. Yes, and it gives you a curved L infinity algebra.
And is it relevant somehow to this or?
No, it's. I mean, okay. The conjecture that in general, whenever you do the different polarization, they should be more equivalent. But yeah, I think I know if it is a theorem in general, but. And even in this example, the idea that you can think of take the corner with one polarization and the corner with another polarization, and you put them together as the two boundaries of a cylinder, and you use the cylinder as a way of constructing this Morita equivalence. Okay, but this involves also extending the boundary fields to bulk fields in appropriate way, checking that it is possible and that it is compatible. So it's not automatic.
In this example, could you prove it?
I think in this example, I think it worked. I mean, I think but yeah, it should work. Yeah. Yes.
What do you mean by Morita?
That there is a bimodule, an invertible bimodule. An invertible bimodule for these P infinity algebras. Well, for these L infinity algebras.
Just Alberto, just to double check that I understand you right. So here you have cotangent of a vector bundle where the vector bundle is over G, right? So you have infinite dimensional.
Oh, yeah, but I think
you have your infinite dimensional vector bundle where the fiber, well.
No, well, I think it actually is a vector space. It's an infinite dimensional vector space.
Okay. Right.
And I take cotangent in.
And what's so it's not a vector bundle. So bundle, it's a bundle of a point, right? Then.
Yes, the point. Yeah.
Over point.
Yeah.
Okay.
Yes. And by cotangent, I mean by a good choice of a dual.
Yes, but when you say different polarization, so you consider instead of omega 1 of gamma tensor G, you consider omega 0
for
of
example.
Gamma tensor G, and you have this double vector bundle.
Exactly.
You have
Yeah, sure. Exactly. Yeah, sure. Exactly. Yeah, sure. And of course, you could also do mixed things, right? You can take A for some subspace of G and C for the complement. I mean, you can do, in principle, other choices. I mean,
Are they Wilson lines?
This?
The corners, the gammas, they're going to be interpreted as Wilson lines?
They could be interpreted as this singularization of the Wilson line. Somehow you should think, I mean, you have the Wilson line in the bulk, they intersect the boundary and say transversally, so they give you some singular point. And the idea is that instead of, working with a singular point, you remove a small disk, and actually since topological, you move like any disk, it doesn't matter. And now your boundary manifold will have a corner which is like the boundary of this disk, this S1. So this is how it is related to the Wilson lines. Okay, so instead of like thinking of the Wilson line, you remove the Wilson line and you get the structure. Somehow the representation you have to put in the Wilson line is related to the representation you choose here for this vertex operator algebra.
Can you like elaborate like a tiny bit when you have this little twiddly arrow quantization, like
elaborate means that you have to do something.
Okay.
yes.
All right,
no,
all right.
no, I just I don't tell you what you have to do. Yes.
Okay, thank you.
Yeah, I mean in this case it's somehow well conceptually easy because the Poisson structure is a of the algebra, so you can do the quantization algebra, so that is the quantization of the algebra, but without the same order. Apologies, the microphone, I believe. Yeah, I mean, depends on what you can start doing. Right. I mean, for Quran, I mean, when you say it is because there is some generative sound that was very nice, you know, called Poisson. That's true. I mean, you're asking the quantization, right? Yeah, the quantization. You know the answer. You have to check the worked out the Poisson vertex algebra.
Well,
They tried.
they worked out in the sense that we know that they're classified by current.
Yes.
But I'm asking, can you
Make it
out
precise.
relate the things?
Yes, it should. Yeah, they should be done. Yeah. I mean, if they're well, yeah, it should be correct. But yeah, I don't know if anybody has done it.
There is a statement that if you take a Poisson vertex algebra.
No, but they have the quantization statement, right? They know that the dequantization. Oh, no, so yeah, sorry. Oh, no, yeah, sorry.
What I'm saying is there are by current, you know that you classify this AT as a three-dimensional model,
Yes.
but also by current you classify specific Poisson vertex algebra.
Yes.
So
Oh, you see, there is this missing link.
they should be related.
Yeah, yeah,
somehow,
sure.
right?
Yeah.
But it hasn't been done.
No, but I mean, what you can do, you can immediately construct the Poisson algebra structure. Now that will be a Poisson infinity algebra structure actually associated to Courant on the corner, and see how it fits in the picture.
Okay.
Yes. Okay, so I have still a few more minutes, right? Yeah, 5 minutes. Yeah. Okay, so now let me just very quickly go through what was the interesting example for us, because this is an example where you, first of all, I mean, this 4-dimensional gravity, 3 + 1 dimensional gravity in the coframe formalism. It's interesting for two reasons. One is because it's an example where you don't go all the way through the reduction because it would be singular. On the other hand, it's interesting because it gives you some algebraic structure associated to the corners of gravity. So the idea now, we have gravity in 3 + 1 dimension, the boundary is 3-dimensional, the corner are 2-dimensional, and on these 2-dimensional manifold, there will be some space of fields with some associated Poisson algebra, Poisson infinity algebra structure. Okay, and of course, this should be related to the various structures, for example, that have been studied for gravity at infinity and so on. Those should arise as somehow specialization of this general construction. Okay, now let me very quickly tell you what are the data here. So the bulk data, so you have to start from the bulk here. So you start from a 4-manifold that admits a Lorentzian structure. And then the other piece of data you have is just a vector bundle over M, which is isomorphic to the tangent bundle, and is endowed with a fiber-wise Minkowski metric. Okay, and this is possible because your manifold admits a Lorentzian structure. Okay, this is sometimes called the fake vector bundle. It's just some choice of vector bundle isomorphic to Tm. There are two fields in the theory. One is a coframe, which is essentially just a choice of an orthonormal basis at each point that you use to construct your metric. And I will view it as a bundle map from the tangent bundle to this V, and I want it to be an isomorphism. Okay, so the two bundles are isomorphic as a choice, but the fields are explicit choices of isomorphisms. Okay, so each isomorphism is a field, a possible field. Okay, so in particulars, you can also see E as a section of the cotangent bundle of M tensor V. Okay, which in particular is not degenerate. And you can recover the usual metric just by pairing E with itself using the fiber-wise metric, or equivalently, you say just it's a pullback by E of eta. You think of it as a section. And the second field you need is a connection for the principal bundle associated to the orthonormal frame bundle of V for some reference Lorentzian structure. And again, I will think of the connection as a section of wedge, a one form taking values in section of wedge 2V. Why wedge 2V? Because the Lie algebra is essentially given by skew-symmetric matrices. So you local one form, yeah. Right. So it's a so locally, yeah. Of course, locally this is not correct, but sorry, no, this is correct. Yeah, you think of them as sections of T star M tensor wedge 2V. Okay. And okay, I will use this notation throughout. Omega KL means section of the kth x0 power of T star M tensor L x0 power of V. So in particular, E will be a 1-1 form under this convention, which is not degenerate, and omega will be a 1-2 form. Then you can form the curvature of omega, which will be a 2-2 form. Yes.
But the connection is not section like this.
No, it's not global. This is just. It's not. Okay, sorry. It's model. The space of connection is so this. Okay. the connection minus some reference connection is a 1-2 form. So here, yeah, too quick to write. Okay, but the curvature is really a 2-2 form. Okay. So what you can do now, you can combine E and F all together. You take wedge product of E with F, and this will be a 4-4 form. And the 4-4 form is canonically identified with the density, and so you can integrate it. Okay, and this is the action that corresponds to Einstein's action in the other formulation. No, you don't need orientation here. Yeah, this is really, yeah. Of course, if you have an orientation, then you identify this. I mean, yeah, it's a bit easier, but actually intrinsically this works without orientation. And another thing you can do is the fourth power of E, because this is also 4-4 form, also density, and this is the cosmological term, which I will not discuss because I have to be very quick. Now, the point that you can compute the Lagrange equation, here you get these two equations. I mean, the variation with respect to E gives you E wedge F equal to 0, and the variation with respect to omega gives you E the omega E equal to 0. Since E is non-degenerate, you see that you can see that you can simplify E here. So you get the equation the omega E equal to 0. That essentially tells you that omega is torsion free. And it has the equation the omega E equal to 0, actually let me go here, as a unique solution. So there is a given E, there is a unique omega of E that solves this equation. And it's actually the one that corresponds to Levi-Civita connection. And then you have the other equation, and this corresponds to Einstein's equation. Okay, so this is the end of the story. And now the point is, what is a boundary structure? So we have probably, I mean, already over time. So I don't know, probably should stop here and talk through this, or can I go, I mean, just 1 minute, just present. Okay, so the idea is that, okay, so what we have to do here now is I will go directly to the boundary and try to describe the symplectic structure of the boundary and the constraints. So it turns out that on the boundary, what you have to do is that, I mean, now you just take the classical action. We know that we do work in the B setting. You take the classical action, but when you take the variation here, you get some boundary term, right? E delta, the covariant derivative of delta omega. And then when you integrate by part, this goes down to the boundary. So this gives you this point here. So this is like what we call the one form is here. So this is what is called the neutral one form in mechanics, right? And its differential is supposed to give you the symplectic structure. Now, these two forms turns out to be degenerate, but you can mod out by its kernel very, very nicely. So you actually get a symplectic structure on the boundary. And moreover, you have this constraint because, I mean, when you take the restriction to the boundary of the Lagrange equation, they still are constraints on the boundary. Okay, so this is analog to what is for Chern-Simons series. In Chern-Simons series, we have a boundary symplectic structure, and the condition that the connection is flat as a constraint. In electrodynamics, you have a boundary symplectic structure, and then you have Gauss law, divergence of the electric field equal to 0 as the constraints on the boundary. Here, the constraints you have on the boundary are these two conditions. Okay, and these two conditions now, well, what you have to do is now to do the BFE construction for this. Okay, the point that here there is some quotient. What you have to do, you have to mod out the connection by 1 to form V that are killed by the wedge product with E. Okay. And the point that you have to write down these constraints on the quotient and a point that they're not invariant. So this is not the good procedure. What you do instead is to take a good section of this quotient where you can explicitly write down these the constraints. Okay. So this works if you make one further assumption. So you assume that the coframe E is such that the boundary metric is non-degenerate. Okay, so in particular, this applies if you require the boundary to be space-like, which is a typical thing you want to think of them as Cauchy surfaces. So in this case, you can see that what you can do is the following. Okay, so first of all, the restriction of V to the boundary, since V is isomorphic to the tangent bundle, on the boundary we'll have some splitting. Here, where I wrote it, probably was in the previous slide. Here, I mean, the restriction of E of the boundary will be something that is isomorphic to the tangent bundle of boundary plus a trivial line bundle, which corresponded to the transversal direction. So what you can do now, you can choose an arbitrary section of this transversal direction, okay? And what you can do is, instead of taking the quotient, as said before, you take one condition that the omega E wedge, this reference section, should be in the image of E wedge something. And you can check that this is a section for those quotient, for that quotient. Okay. So this is an explicit description. And then there you can just write down the constraints. And then you can do the BVFE formulas as before. It turns out, this is another nice thing, is that on this space, it turns out that the constraint d omega E equal to 0 is equivalent to E d omega E equal to 0. This will not be true in general on the boundary, but it's true under that condition. And so now you do the BFV formalism, just introducing the appropriate ghosts and as Lagrange multiplier of the two conditions. So these are the things you have to do. And now, well, you can fill in the dots. This is a bit complicated, but you can do it. And then you can do the procedure I described and go to the corner. Maybe just let me jump to the result that you go to the corner. And on the corner, you get some interesting structure, maybe, which is here. You get these you get some degenerate two form, one form here, and an appropriate vector field. And just let me mention very quickly, a simplified structure can be described explicitly. Essentially, okay, that's just me say here, this ghost mu here that you need for these equations is actually a section of V. So you can expand it in the basis given by E and En. And so you represent it in terms of a vector field psi and some function psi n, which you used to think of as transversal vector field. So now in this simplified description, I just set them to 0. And it turns out that you get a very explicit construction for the symplectic structure. So basically the only boundary fields here now are just given by the coframe E and the ghost C, the connection omega, and the tangent component of this vector field psi with this explicit form for the function of degree 2. And out of it, you can try to get information about the associated Poisson infinity structure. And this turns out to be, in this example, essentially related to the Poisson algebra on the dual of a section of an Atiyah algebroid. So there is an associated Atiyah algebroid, which is given by well, the vector bundle we had for the SO31 structure and the tangent bundle to the corner. Okay, and this is somehow already captured by the simplified picture. Okay.
Thanks a lot. Do you have any further questions?
Yes. Well, that's interesting. Yes, I mean, already in this simplified structure, the quantization would be interesting, and I mean, yeah, it has to be studied. Yeah, I mean, I ask you at some point. I mean, again, in this case, in this simplified case, it is a dual of some Lie algebra. So, in particular, you're interested in representations of these infinite dimensional Lie algebra. Actually, it's a bit more interesting because what you get